In this section, we'll be taking a look at inductive and deductive reasoning. So, when it comes to types of reasonings, there are two main types of reasonings, the ones that I just mentioned. And we're going to take a look at some specific examples of some of these. So, in this example, let's predict the number, the next number in the following list. So the numbers are 10, 14, 18, 22, 26, and we want to know what is the following number. So hopefully what you might notice from here is that these numbers are always going up by 4. And so what you would hope is that this pattern would continue, and the next number should also just follow the previous one by adding 4, and that our next number should hence be 30. So what we're really doing here is we're examining some pattern. So we're looking for a pattern in the numbers, and then we're assuming that this pattern will hold, will continue. We're not being told that the pattern continues. We're just sort of making that assumption ourselves, and then making a conclusion based off of that. And this type of reasoning is called inductive reasoning. It's the process of reaching a general conclusion by examining specific examples. So in the list one, we examined the specific examples of what numbers are in the list. We found a pattern that was possibly a consequence of those examples. And then we concluded that that pattern is going to continue, most likely, and made a conclusion from that. So I recommend pausing the video here and answering the following question yourselves. Use inductive reasoning to predict the next number in the following lists. 3, 6, 12, 24, 48 comes after. And then slightly more challenging, 3, 5, 8, 12, 17 comes after that. So I'll give you a couple seconds to pause the video, and then I will go over. So in the first example, you might think of this additively. You might think like, all right, well, what do I have to add to 3 to get to 6? Well, you could add 3, but then you would add 6 to the next one, and then you would add 12 to the next one. And sure, there is kind of a pattern here, but it's much easier to just notice a pattern of saying that these are just always doubling. So each of these numbers we're just doubling to get to the next entry in the list. And so if our last entry is 48, then we should double that to get the number 96, which should come afterwards. In part B, let's think of it additively. So we're adding 2, we're adding 3, we're adding 4, we're adding 5. Hopefully it should come as no surprise that what I would conclude the pattern would be here is that the next number we should add would be 6. So just the number that we're going up by themselves, these numbers are all going up by 1. So you can maybe like notice like as a pattern, or view it as a pattern in that sort of way. There's like a table of like second differences. We'll see more examples of that in the coming section. And yeah, so assuming that that conclusion continues, we should conclude that our next number would be 23. Some pros and cons of this type of reasoning. A pro is that it's a pretty simple approach. All you have to do is just kind of look at some examples, find a pattern. Hopefully that pattern is easy to recognize. If it's not, obviously that'll complicate the problem. But the approach itself is kind of simple, of just look for a pattern and extend the pattern, generally speaking. You can use this to make conjectures as well. So even if you are trying to be like a little bit more rigorous in your reasoning, like you still need to kind of have a guess for what your answer should be. So maybe in the previous examples, you are unhappy with the fact that we are just like, we're not being told that the pattern continues at all. We're just sort of assuming for ourselves that the pattern has to continue. So if you are sort of unhappy with that, that's actually fine. But like, it's still good to have a guess or a prediction. Often call this a conjecture for what the answer should be based off of what's going on so far. So using this type of reasoning to make conjectures about what the answer should be, and then proceeding from there to be like a little bit more rigorous, is a really beneficial thing to do, and happens all the time. Like even like in the highest levels of math and science and all kinds of stuff like that. As for cons, sort of what I was hinting at already is that it requires you to make an assumption that is not being told to you. So this is kind of like a leap of faith that is being made here. We're just, in the list of numbers examples, like we are just sort of hoping that the pattern has to continue of like, oh, we just add 4 every time. And if that assumption is actually not correct, then we might not reach the correct conclusion. So this obviously just does not always work as a result, because our assumptions could be wrong. All right, counting regions. So let's complete the following table. So I should explain what's going on here first. So our setup is that we're going to have a circle, and on the circle, we're going to have some number of dots on the outside. So we're going to start with just 1 dot. And then we're going to draw a line from every dot on the circle to every other dot on the circle. So if I were to have a second dot on the circle, let's put it like right here, I draw a line from the first dot to the second dot, and then I count the number of regions that I have created. All right, now technically you could be like stupid and you could like double up a dot, and then like that would sort of create like the same number of regions. And so or maybe you have like a situation where if you draw all 3 lines, you could have something like this, or you could have something like this where you create like different numbers of regions. So you have something like that, and you have something like that. These create different numbers of regions. This would have 6, this would have 7 regions. So let's just be simple and just say the maximum number of regions that you can get when doing this. All right, so let's fill in this table. So right here we have 2 dots on there. Let's copy, paste this a couple times. If we just had 1 dot, then there's only going to be like 1 region, because we're not really drawing any lines. So 1 dot, 1 region, 2 dots, 2 regions. Let's draw 3 dots. Boop. Draw that. Draw that. If we count right here, 1, 2, 3, 4, we'll get 4 regions. Wish I made these black. Let's just make it like that. Okay. Let's keep going. Let's draw a 4th dot right here. And then we'll draw lines from this dot to every other dot, and then count again the number of regions. So 1, 2, 3, 4, 5, 6, 7, 8. So now we have 8 regions. Okay, so it looks like we're just gonna hopefully keep on doubling. And let's keep going just to make sure that that pattern does seem to be continuing. So again, just drawing line from this dot to every other dot. And at this point, it's starting to get a little bit messy. But again, let's just count how many regions just to be sure. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we have 16 regions here. All right, so it really looks like we're just doubling every time. But the table tells us to draw 16. So at this point, we can kind of just guess that like the number of regions for 6 dots should be 32. If I were to just sort of fill this out right here, this would be using inductive reasoning, right? My inductive reasoning would tell me that if I were to use 6 dots, then, well, just based off of how this table has been going so far, then the number of regions that I should have for 6 dots should just double as well. So that is inductive reasoning because we are making an assumption about how this table is going to keep going. We're assuming that the pattern of just the number of regions doubles every time. We're just assuming that that pattern holds. Okay, and it's good to double check your conjecture. So let's actually do this. So I'll draw this in blue just because it's getting pretty messy at this point. And then let's count. So 1, 2, 3, 4, 5, 6 so far. 7, 8, 9, 10, 11, 12, 13, 14. There's a little bit of a problem right here. Let's so at this point right here, like I have that like triple line crossing that I said that I wanted to specifically avoid. So let's actually like kind of scoot this all over a little bit just so I don't have any of the triple crossing showing up in my diagram. Let's see, are we avoiding all triple crosses? No, yeah, okay, cool. All right, now let's get back to counting. So we had 1, 2, 3, 4, 5, 6 down here. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. So it seems like our guess of 32 was actually wrong, and that the number up here should actually be 31, which is very surprising. And so it seems like our process of inductive reasoning actually ended up being incorrect, right? So this is, like I was saying over here, it requires some leap of faith to be made, an assumption that the pattern is always going to hold. And that pattern, you might just be wrong sometimes. That pattern just might not hold sometimes. And it doesn't in this case. The pattern breaks once you start having a 6th dot right here. And so that's really unfortunate, but it just kind of works out that way. All right. So on that note, counterexamples. So counterexamples are usually to logical statements. Logical statements, things like all dogs are black, or all cats have fur, or if you are a human, then you have at least one eyeball, or something like that. These are all examples of logical statements, things that involve if, then, for all, there exists. These are examples of logical statements. And so how do you prove or show that something is like true or false? So showing that something is true is a little bit harder than showing something is false. If I'm saying all dogs are black or something, that is inherently easier to disprove, because all you have to do is just show me a dog that is not black. Come up and be like, oh, hey, look at this Chihuahua. It has like gray fur, right? This is an example that disproves your example. You just need to provide a single counterexample. If I'm trying to say all cats have fur, that is harder to prove whether or not it's true or false. Okay, you could have like one of those like naked cats, so maybe that's not a good example. All humans have a heart. That one is much harder to prove is true, because in order to prove that it's true, you would have to say something about like, all right, this is every single human in the world, and if I look at every single one of them, then each of them has a heart. And like you have to just kind of hope that there's no counterexample. So proving something is false is much easier inherently. But let's just look at how to do that. And really all it comes down to is just providing a counterexample. So let's disprove the following statement, but just by providing a counterexample. For any number x, x over x plus 3 is equal to 1 over 3. So this is a common algebra mistake that I'll see, like even in classes like calculus or whatever. People will just kind of think like, oh, well, I can just cancel out the x's right there, and then I would have just like left with like a 1 and a 3 in there. So this is false, because you can just consider a counterexample of like, well, let's make x equals 1, then x over x plus 3 in this case is equal to 1 over 1 plus 3, which is equal to 1/4. This is different from a third, so you don't get that. Maybe you might think like, oh, the answer should be like 1 over 4 always then. Well, it's, disprove that as well. So if I do x equals 2, then I would have x over x plus 3 is equal to 2 over 2 plus 3. So that's equal to 2 over 5. And 2 over 5 is not equal to 1 over 4. These are both like in simplest term fractions, and they are different from each other. Therefore, this is just not a cancellation that you can do. Okay, here's 2 more. I recommend pausing the video and attempting these problems on your own. For any numbers x and y, x plus y squared is equal to x squared plus y squared. And then for any numbers x and y, 1 over x plus y is equal to 1 over x plus 1 over y. So if you feel like you're able to attempt that, pause the video and give those a shot, and then unpause, we'll go over. If you feel like you need a little bit more of a push, I'm going to do part B right now. So maybe watch me do part B and then pause the video and try part C on your own. But let's start with part B now. So let's just pick numbers. It doesn't really matter which numbers we pick. So let's just kind of, all right. So sometimes if you pick like numbers and you do get that it works, that's okay. So x plus y squared in this case would be like 0 plus 1 squared. That's just equal to 1 squared. And then what is the right-hand side of our equation say? Well, x squared plus y squared here would be 0 squared plus 1 squared. That's equal to 0 plus 1. So 1 squared is equal to 1, 0 plus 1 is equal to 1. These two things are equal to each other. So this is actually evidence to say that this is a true statement, right? So this tells us that this is just not enough information to conclude anything. So what we have to do is actually pick different numbers. All right, so let's pick different numbers and see what happens. So let's pick x equals 1 and y equals 2. So if I have x plus y squared for 1 and 2, that would be 1 plus 2 squared. So that's equal to 3 squared, which is equal to 9. If I were to do 1 squared plus 2 squared, it's equal to 1 plus 4, which is equal to 5. And these are, in this situation, not equal to each other. So this is a valid counterexample, even though it does sometimes work for some values of x and y. It doesn't happen for any number of x and y. This is telling us like, no matter which x and y that I pick, this has to always be true. But this pair of counterexamples right here disproves it. All right, so So maybe pause and attempt C on your own if you have not done so already. I'm going to go ahead and do it myself. Let's stick with the same values of 1 and 2 and just see if it works. I don't know whether or not it will. I'm just kind of picking numbers and seeing what we get. So I'll do 1 over x plus y and then 1 over x plus 1 over y. 1 over x plus y here is just 1 over 1 plus 2. That's just 1 over 3. 1 over 1 plus 1 over 2, that's equal to 1 plus a half. Or you could combine this, find a common denominator. This is like 2 over 2 plus 1 over 2, which is equal to 3 over 2. And these numbers right here are not equal. Okay, so x equals 1 and y equals 2. This would be a counterexample. All right, let's finally get on to deductive reasoning, which was the other type of reasoning. So I'm going to illustrate this just by doing a math magic trick that you might like show to like your 5-year-old niece or nephew or something like that to blow their mind or whatever. So pick a number, just have a number in your head. Take that number and multiply it by 3. You'll have a new number. And that number you want to add 6 to. All right, so pick a number, multiply by 3, add 6. That new number that you have, now divide it by 3. Think about what you have, and think about what you started with, and subtract that number that you started with whatever the number that you had up to this point. And then see what number that you got. So the magic trick is to just say like, oh, if you did all these steps correctly, then your final answer should be 2. Right, so if I were to pick a number of 4, multiply it by 3, I get 12. Add 6, I'm at 18. Divide by 3, 18 divided by 3 is 6. And then subtract 6 minus 4, which was our original number, we end up with 2. Okay, let's try it for a different number. Let's maybe pick like a 2-digit number, see if it works for that. So let's do 11, multiply by 3, I get 33. Add 6, I'm at 39. Divide by 3, 39 divided by 3 is 13. 13 minus our original number 11, 13 minus 11 is 2. So we get the same thing. All right, let's just do for one more. I'll do it like kind of quickly. Let's do like 100. Just 'cause. So multiply by 3, add 6, divide by 3, subtract 100, and we get to 2 again. So if I were to use inductive reasoning here, it looks like no matter which number I pick, I'm always going to get 2. So we're still using inductive reasoning, just sort of examining a couple of specific examples and saying like, oh, we're always getting to 2. But this inductive reasoning, as we've discussed so far, does not prove that this is going to always work. Like maybe this is a thing that only works for like up to 3-digit numbers. Maybe if I were to pick like 9,764, maybe this number, it would fail. You never know. So deductive reasoning says, well, you need to be able to justify it fully. So let's say that like, let's introduce a variable here. Let's call our original number x, and then just follow what we get by just applying this procedure of we multiply by 3, add 6, etc. So if I multiply x by 3, now I'm at 3x. If I add 6 to that, I'm at 3x plus 6. If I divide that by 3, I'm getting a third of 3x plus 6. And then if I subtract my original number, I'm just subtracting x and then seeing what I get. So does this number always equal 2? Well, we can just take this expression right here and just simplify it. So 1/3 of 3x plus 6 minus x, that is equal to, well, if I distribute this 1/3 to all of the terms, then I would get 1/3 of 3x is equal to x. plus a third of 6 is equal to 2. So I get x plus 2 minus x. Now those x's will cancel, and we're left with 2. So regardless of what number we started with x, our final step is always going to be equal to 2. And so this is an example of deductive reasoning, which is the process of reaching a conclusion by applying general assumptions, procedures, or principles. So we are just purely using logic and math in this example of we're saying, like, all right, well, you had to have some number. That's not really an assumption. And we're being told this procedure has to happen, right? So we're not making an assumption about what the procedure looks like. We are being told this is the procedure. And if you apply this procedure to this number x, no matter what x is, this could be like 2.57 or something like that, you're still going to end up at the number 2 at the end regardless. Okay, so we're reaching a conclusion by applying general assumptions, procedures, or principles. In this case, we're applying a procedure and then reaching that conclusion. So just again, to summarize, inductive reasoning, we tried a few numbers and we guessed that the answer should always be 2. Deductive reasoning would be start with calling our original guess x, follow the steps exactly, and deduce that the final answer must be 2. Pros and cons. Pros is that the conclusion is guaranteed to be true. Right. However, some cons, it can be harder to reach that conclusion here. So the inductive reasoning in the previous case, we just have to try a couple of numbers, and then just, based off of that, just be like, all right, well, it seems like we're always getting 2. And so it's likely that the answer is always 2. But doing the deductive reasoning to make that conclusion was a little bit harder, of like we have to introduce a variable and then do some algebraic steps. If you mess up your algebra along the way, that introduces some challenges potentially, depending on how complicated your problem is. So it's a little harder. And it requires your assumptions to still be valid. So this is so this bullet here doesn't really apply to that previous example. It'll make more sense in some like real world examples. Yeah, let's actually come back to that. So, all right. Example 6, determine whether the following arguments are using inductive or deductive reasoning. So I just recommend pausing the video and just thinking to yourself whether it's using inductive or deductive reasoning. So part A, all children love cartoons. Jill is a child, therefore Jill loves cartoons. Is this using inductive or deductive reasoning? So I'm going to assume that you have paused and thought about this sufficiently. So if we are being told the information that all children love cartoons, and Jill is a child, therefore we can conclude, well, if Jill is a child and all children love cartoons, then Jill must love cartoons. So that is an example of deductive reasoning, because going back to the definition, here we go. We're reaching a conclusion by applying our general assumptions, procedures, and principles. So we are applying the assumption that is given to us and then reasoning from those assumptions that Jill must love cartoons. In part B, my orchid has bloomed every other February since I got it. It bloomed last February, so this February it won't bloom. Right? Every other February it's blooming. If it's alternating and last year it did bloom, that means that this year it doesn't bloom. Is that inductive or deductive reasoning? So I'll give you like 5 or 10 seconds to pause, think about it, and come back to this. So here, we are not being told like any assumptions that we are supposed to make about the orchid. We're just kind of we're just kind of given what's happened, some information about what's happened in the past. We're kind of given like some examples of, so far in the lifespan of the orchid, it's bloomed every other February. But we have to make that leap of faith of assuming that this pattern is going to continue in order to make the conclusion that this February it will not bloom. So this would be an example of inductive reasoning because we are making that assumption on our own. So one of those key differences is that in deductive reasoning, we are being told the assumptions that we are supposed to make. So the logical statement that kind of comes along with this is that if these assumptions are true, then this conclusion is true, right? If all children love cartoons and Jill is a child, then we can conclude that Jill loves cartoons. You could turn this statement into a logical statement. You could turn this into saying, if the orchid blooms every other February and it did not bloom last February, then this February it will not bloom. So you could kind of turn this into a something where you could make a deductive argument. But as it's written right now, you are making the assumption on your own. The assumption is not being given to you, and so this is inductive reasoning. So coming back to that last con, a con of deductive reasoning is that it requires your assumptions to be valid in order to actually apply it. So in this cartoons example, it might not necessarily be true that all children love cartoons. So this just sort of by itself, there are some kids out there that don't really love cartoons. And so if you're making this assumption that all children love cartoons, that assumption might not be valid. And because that assumption is not actually valid, then you couldn't really apply this statement to the real world necessarily, right? So this statement is true logically speaking, but that doesn't necessarily mean that you could apply it to the real world. Okay, so that is it for inductive versus deductive reasoning. Let me know if you have any questions about this, and I'll see you in the